Okay, now if I copied this right here, so basically the Z right there, the R right there, and the rho right there, and there's the angle phi. If I take this R and mimic that right there, and if I look at this triangle, this is R. If I look at the angle phi, if I look at the angle phi, so I'm looking at something like this. It doesn't look as pretty, but it's okay, it'll do the job. So first things first, if I take the sine of phi, that would be the opposite, which is r over the hypotenuse, which is rho, which indicate that r is sine of phi times rho. And if I look at this right triangle, I forgot to mention, this was z, I'm sorry. This was z, right? If this is z, then this is z. Well, wouldn't that say right there that rho squared equals z squared plus r squared? And wasn't r squared, wasn't that x squared plus y squared? And I know that x is r times the cosine of theta, and I know that y is r times the sine of theta. I know that from x and y and r. But now that I know what r is, so I know that x is rho the sine of phi times the cosine of theta, and y is rho times the sine of phi sine of theta. And here they are. And that's how you connect those back and forth. Now if you take rho, sometimes you see it as the square root of z squared plus x squared plus y squared, or square root of z squared plus r squared. So here the catch is to move back and forth. Now I'm going to be honest with you. If I do not see a sphere, I really wouldn't even attempt using spherical coordinates because there'll be a lot of work. But on a sphere, it seems this is much simpler to apply and use. Just double checking what I gave you so far. Cylindrical, and here we are. Whoops. So in the first batch of problems, I'm trying to figure out what these graphs look like. To sketch the graph described by the following spherical coordinates in 3 dimensions. Again, if you could just see the graph, pretty much you could do the calculus. Visual is a must. So if I glance at the 3 dimensions, it's hard to convert rho. It's not impossible, but it's a lot of work. But notice what this is saying. I'm sorry, phi. Phi equal pi over 6. If phi was to drop down roughly 30 degrees, 2 things they're telling us. They're saying rho could be any number. Rho could be any number, which means rho takes on any value all the way to infinity. And theta could be anything. Theta is going to take that and it's going to rotate 360 degrees, creating an infinite cone. The cone doesn't stop there, but just to show it. This is an infinite cone. Starting at the origin and running up, since rho is always positive. Rho equal the square root of, it's not like r. R could be plus or minus, but not rho. Another problem we want to figure out, well, we're trying to figure out what this looked like, kind of like what we did back in the days in polar coordinates. We're trying to eliminate those. So there is no secant. That's 1 over the sine of phi. And that is rho sine of phi equal 1. And if I try to match What does rho sine of phi equal? Well, it's right there. Basically, what this is saying, if I convert that to r and theta, this is saying r equal 1. Do I know what the graph of r equal 1 mean? Well, in two dimensions, it was a circle. On the floor, it's one of those. But if I was converting this to cylindrical coordinates, it would look like an infinite cylinder, because rho is not there, and z could be any number it wants. Same deal here, you know, phi takes on all the values from 0 all the way down to pi. Rho is fixed to be based on that, but then there is no restriction on theta. Number 20 is a problem you really want to pay attention to. This is really the main use of those. You see a sphere or a portion of a sphere, you need to identify it first. And when they say rho runs between 0 and 1, well, rho runs between 0 and 1. It takes on all of these values all the way to 1. Now, phi runs from pi over 2 to pi. I'll get to that in a minute. And theta runs between 0 and pi. Well, theta runs between 0 and pi in two dimensions. That's like this. That's like running from this to this kind of, sort of speak, right? In that direction. But pi over 2 to pi, if phi equals 0, I'm right there. If phi equals pi over 2, I'm right there. So this starts right here and traces down to the bottom. So the actual length of 1 is not going to be there. It's going to actually be right there, 1, and it's going to run all the way down, right? And what's going to happen as this runs back and forth? This is going to run up and down, creating, now I made that way too big. If I go 1 and 1, and what is that going to create? A quarter of a sphere. Do we see that? Think of a sphere. Think of an orange, and you chop it. Think of an orange. You chop it halfway there and halfway there. And this right here is the quarter corresponding to that if you are seeing an actual sphere. So as far as calculus is concerned, well, if I want to find dv, that's dx, dy, dz. If I want to go for cylindrical coordinates, dz is identical, and I know that dA is r dr d theta. And if I want to go for spherical coordinates, then dv, which is dx, dy, dz, if I replace everything with what it equals accordingly, that's what I end up with, that extra factor. Now, if I look at the triple integral over region D of f of dv, if I want to go for cylindrical coordinates, there it is. And if I want to go for spherical coordinates, there it is. I do provide this on the test. You really don't need to memorize that. We'll talk more about that in our class discussion. Now we want to apply some of these problems. Look at number 24. It says evaluate the cylindrical coordinates. This doesn't vary much from what we did. If I run this in terms of z first, well, that's going to be what? Z evaluated from r squared over 3 to square root of 18 minus r squared. That's going to be the square root of 18 minus r squared over 2. And we're going to do this r dr d theta, integrating from 0 to 2 pi theta and 0 to 3. And I'm assuming you could finish that up. And if you can't, let me know during the discussion. I'll be more than happy to show you that. I'm trying to finish as many as I can within the next 5 minutes. Keeping in mind, when you distribute this in, this is really the square root of 18 minus r squared times r, and this is r cubed over 3. So this is a u sub, and this is add 1 to the power divided by that. If I look at number 28, another problem, the same deal really. There's not much to those. This is very close to what we did. As far as z is concerned, this is z times r squared, the sine squared of theta, plus z cubed over 3 evaluated from negative 1/2 to positive 1/2. You plug those in. And remember, you're not doing both of those one shot. And here you're going to get negative 1/2 r squared, the sine squared of theta, minus 1 over 8 over 3. And remember, you're going to integrate that now with respect r dr from 0 to 1. That's this part. And then here, you're just worrying about the r. You're not worrying about the sine squared. That's left at the end. And when you get to that, how do we evaluate sine squared? We use power reduction. That's 1 minus the cosine of 2 theta divided by 2. So you're doing those individually, not combined. It's not like the parts or anything like that. And I'm going to assume we could finish this one. Again, whatever you can't integrate, I'll be more than happy to show you during the class discussion. On the next problem, this is number 40, directions set up an iterated integral to evaluate the triple integral over region D of f of r theta z dz r dr d theta. And to us, that's going to be the integral of, and let's see how this plays. Z runs from the ground down and exit out of this plane 3 minus y, but we won't know that y is r times the sine of theta. Now, I need to worry about this part. And if I put that, there's the x-axis, there's the y-axis, and doesn't that region look like this? In which this right here is r equal the cosine of theta, a circle centered around the positive x-axis with a diameter of 1, and this is r equal twice the cosine of theta. And how did we do this back in the days? Well, we ran r dr d theta. We say theta runs from negative pi over 2 to pi over 2, just like we did in the previous class. And r runs from what? R runs from the cosine of theta and terminate at twice cosine of theta. On number 44, we're supposed to use spherical coordinates. So if I really look at this as follows, 0 to 2 pi, 0 to pi over 4, 0 to 2, and if I just multiply those out, that's phi cubed cosine of phi sine of phi d rho d phi d theta, and I could see clearly that add 1 to the power divided by that. I know this is the sine of 2 phi divided by 2. I can integrate that and proceed and finish the problem. Again, anything you can integrate, ask me tomorrow. I'll be more than happy to show you. And on this last problem, it says, find the spherical coordinate limits for the integral. Evaluate. I want to set up the integral. This would be the integral. Automatically, if I'm using spherical coordinates, I'm going to pick a rho squared sine of phi d rho d phi d theta. And let's glance at this. Let's get those one at a time. Do you notice that theta runs all around? That takes care of that. Phi is the tricky part, not because it's hard, because you're not used to it. If I look at phi, I notice phi starts from pi over 3 and terminates at pi over 2. Remember, this is phi equals 0. And if I look at a row, it tells me right there that this row is running from 0 all the way to 2. And that would be it. And here's the homework.